Good morning, everyone. I hope all of you are doing fine. I'm also doing better. So, we continue our discussion, which we were looking at a new way of discovering the subjects which are people, or let's say the industry and the communities exploring. And so, we will talk about those and we will talk about the rationale, and then we'll also talk about any advancements in this particular technology. So, for today, we will look at what. So I hope all of you know DRAM. We have talked about it in multiple videos, right? What is which you know typically as RAM in your computers, right? Which has, as we talked about, as of now, it has a transistor and a capacitor, right? This is the basic building block of a DRAM cell, right? Where the charge, this is behaving like a switch. Your transistor and your capacitor stores the data. But we also saw, because this transistor comes with a leakage, that means that there is going to be some leakage which is happening in the capacitor, right, with time. And that is why you may lose data after certain time, right? And that is why there is something called refreshing, which is needed of the data in DRAMs, right? That is the idea. So we can see, though it is non-volatile, but it is not truly non-volatile, because the data cannot stay for long because of the MOSFET leakage, right? So it's not truly non-volatile, right? And the reason is that you see your data is leaking. So now the question we are asking is, and you know that this RAM is very important for AI and everything. If you see, this can come in the form of, which you, if you hear in AI systems something called high bandwidth memory, it's nothing, it's just the DRAM chips which are stacked on top of each other, right? That is what is making these HBM cubes, or right. So these DRAM chips which are put on top of each other is making this high bandwidth memory. So you see, it is becoming more and more important for any applications related to ML, AI, and all the AI hardware systems, right? So then the question is that, okay, this is good. The only thing which we see is a problem is the refreshing, right? This has a refreshing problem, but that is not all. There is another problem, which is when we are putting this DRAM, you see there are two things which you have to put. First, you have to put a transistor here, right? So suppose a transistor may look like, as we have seen, is right, your oxide, your metal, right? And these are your pockets or whatever your transistor is. And then with this transistor, as we saw source and drain, here what we will do at the source and drain, because there is another metal which you are getting on the top. So what you would do is you would basically fabricate a capacitor also, and these are the capacitor which are fabricated typically through trench. That means these are MIM capacitor, in the sense that there is a metal. So let's say this metal is connected here, right? Then there is a dielectric. So this is your metal, let's say, right? This is your then dielectric or oxide, and then there is this metal, right? Fill in the. So this is the MIM kind of cap which you are building with the. So this is the cap which is there in the DRAMs. But as we see that we need to have more and more scaling, this maintaining this cap could be a problem, because you know that C basically is epsilon A by D, right? D is you can control, but you can only, because we have seen already that the oxide, so if you are seeing a metal and oxide and metal, right, this kind of thing, you see that oxide can be scaled to only certain extent, right? It cannot be really. So if this is, let's say, whatever dielectric we are using, silicon dioxide or any other dielectric, you see that this can be scaled to, or as of now, let's say HFO2, this can be scaled to any particular thickness, right? It cannot be scaled below that. And the reason is because then you start seeing, if T dielectric or TOX goes down, your quantum tunneling becomes a problem, which you don't want in a you don't want any leakage in your capacitor, right? You don't want a leaky capacitor. So then, in the sense that oxide thickness is one key criteria which you cannot reduce as you want, right? And so then the question becomes that what can we do about it, right? And you see, okay, we can increase the area. If D cannot be done, we can increase the area, or we can play with epsilon. So epsilon is already, let's say if we are using around HFO2, which is around 20 to 25 epsilon, right? So then, yeah, you have already reaching that limit of, or you could find any other high K, very high K material. That is another possibility which people will be working on, or the industry would always be looking for other high K material to integrate with the metals, right? So that, which are CMOS compatible, so that you can achieve this higher capacitance. That is obviously another is area, right? And area, you see that because we don't have much space here, so area you would have liked. So area, when we talk about of a capacitor, is this area we are talking about, right? Um, so you see that this is the area we are talking about, W and this L, that's it, right? So now this W and L is what cannot be large, and the reason is clear because large A, right, W by L planar, or let's say planar W into L, if it is large, then it is going to take a lot of silicon area, right? So silicon penalty you are going to get. So then obviously the one thing which comes is, if you want to increase an area and you cannot really deal with silicon, the one approach is to trench, right? Because there you don't lose silicon area. You lose, basically you are kind of utilizing the trench of the silicon, or you are utilizing, let's say, the vertical dimension of the thing. And that is what is done here, where you see that you have this metal which is going like this, and you have your dielectric, right? And you have metal. So this is your metal, this is your metal, right? And this is your oxide. So now you see that how you are at the distance between the two is still D, but how you are utilizing the area is by this trench. So let's say if you put this is the height of your capacitor, and whatever is the width. So you see that you're already, your area or the length in the trench is 2h, around 2h, and whatever, let's say this W is, right? So 2h plus W is your width, or sorry, length of your thing, and whatever then you are repeating in this direction, right, would give you the uh, so if you have space in this direction, which is, let's say, let's call it width, right? Let's call this, so this is nearly 2h, right, the length. But you see that now, because of the trench, the area becomes like nearly 2h, because this, whatever this is very smaller than h. So 2h into W, right? Which is now, if you can increase the trench width, you see that you can increase the area without creating any penalty, because it's all in the trench, right? This capacitor. So that is one challenge, and or whatever is going on in the DRAM community, that you want to increase without giving a penalty on your capacitance. You want to still scale this, right, with each generation. That's how you can fit in more and more cell. That is the whole idea, right? So now in that space, basically there is another memory which comes in with a um, advantages, which is saying, okay, if DRAM for this, that I need a separate capacitor and transistor, is it possible to merge them? Because then I can save a lot of area. That means then I don't have to make two separate components, which is MOSFET and then cap, right? This would not be two separate components which I have to make on a area. Is it possible that I can get the similar kind of memory uh, property, right, which I can store the data, but I still do not pay penalty in the area? So that is where the concept of that, we, rather than doing this cap, we put this cap in a way inside, or this information, what we say, or of 1 and 0 is put, or is utilized. So it's built, right? This 1 and 0, basically you are building using a ferroelectric. And the idea is simple here, that simple in the sense from the point of view of looking at it. So let's say this is your normal oxide, what you were having initially. Here you put a ferro, right? And this is metal. So what you did when you put a ferro, you know that when you apply, let's say positive here, right, which is let's say electric field in this direction, this ferro is not, so if we see the polarization of the charge in the ferro, which is, let's say, polarization, right, which gives you the charge. So, right, and this is your electric field, right? These are what you are applying. So when you see that typically we have talked about it in a normal insulator, this would go like this and come back like this, right? That's how the polarization is, right? So this is the, what is the conventional dielectric? Because every dielectric has this polarization, right? When you apply electric field, you see your electron cloud and the positive charge, they go away, but they are still bound together, but they are polarized, right? That is what the polarization mean. Uh, so then in that case, we see that this comes back like this, right? There is no memory, or say when as soon as we remove the electric field from this oxide or conventional dielectric, you see that you come back right to the normal state, right? So that is what is happening in a conventional dielectric. But what is very distinct, which happens in a ferroelectric, is it goes there, and then what it does is that it retains that information, right? It does not lose the polarization. So that means polarization remains there, right? And then when you apply the reverse field, what it does is obviously polarization stops or starts to go down. At some field it becomes zero, right? And then it goes into the opposite direction. And then what it does is, if you now remove the field from this, it comes back again, but it does not come to zero. And then it goes back again, and then like this, right? So what it is doing, and this is the basic property of a ferroelectric uh, layer, right? Or a ferroelectric dielectric, right? Ferroelectric oxide, let's call it, right? And this is the property, because what you do is, now you see whenever you remove even the electric field, you have two, there's a positive or negative polarization which you could have, right? And what that does is, that means even if the field is not there, you have some way to store information, because this is two distinct state, right, of your MOSFET. So what is happening in MOSFET as a result of it, as soon as you remove, right, there is either, because if there is a polarization which is there inside, that means polarization, for example, so we can take it, let's say when we are applying this way, that the electron is going and this positive is going this way. Let's say this is one polarization of the ferro, right? So now if this polarization there, you know that this positive charge will be here, right? In oxide also it would attract the opposite thing, right, which is, let's say, negative here, positive here, and then it would attract electrons here, right? That is what is going to happen when you have this kind of state. But we said that, oh, this is not the only state you are having, right? So you say, okay, this is the state, we call it, let's say, plus PR. Then you say there is another state which is possible, which you just said is the minus PR, right? This is also possible, you're saying. So if that is happening, then you see in oxide what is the opposite is going to happen. And when this opposite happen, now you see electrons are not there, right? So electrons will go away, right? So less electrons and more electrons is what is the state you will see in two different polarization of your MOSFET. And that is a very important piece of information, because that is going to change your current, or what we can say is the threshold voltage of your MOSFET, right? So that means in two states, if I were to draw the IV of the IV is obviously drawn with the two contacts, right? This V is applied, and then we see this is VDS we are applying, right? And then what you are going to see that, or let's say VGS, because uh, we can see the threshold voltage, how that changes. So let's say in one state you were seeing that, because you had to, the electrons were already there, so it was much easier to apply or to go to the inversion, right? This was the, let me draw with the same color which we drew there, right? So This was when the electrons were there, we saw this was there. But now, because you see that there's a different polarization, if it goes to, then it does not come back with this, right? So there is a different, because the electrons have gone away. So that means the threshold voltage has shifted, right, to this. So let's say this is plus PR to minus PR, whatever. You have two states, you have two different threshold voltages and two different currents for the same, let's say, or for, two different gate voltages for the same current, right? Or for the same current, same voltage, two different currents. And that is the effectively coming from your ferroelectric, right? That is what is building this ferroelectric. And you see that with this one device, you are able to actually build a memory cell, right? So this can behave like a memory cell, right? And so that means if now the only thing which was left there is that can you integrate this, because we are anyway making the MOSFET. So can you integrate this ferroelectric into the current process, and does it really behave, give you the same performance as the DRAM? And the performance by which you mean is something called, obviously, at a time. There are three different things we have talked about. Memory is a time, that how much time you are taking to read, write, right? All those operation which you do of the read access, write access, all those time, right? And then there comes the energy, obviously, how much energy you are spending to enable it, right? Because you need to have the same voltages as your MOSFET. You cannot have very high voltages here, because if you have very high voltages to do all of that, then you are losing again energy, right? So that is another. And the third thing which comes is here, which is the robustness or the reliability, in a sense that you are going to operate this over number of cycles, right? So when you are going to do it over number of cycles, you get still the same threshold shift which you require. So that is the called the reliability, and that is the key figure of merits one sees that one net needs to take care of if they are looking at that what could be, what could augment, right? RAM or DRAM, augment or replace, right? I mean, it could replace also, depending on which gives you better, or replace DRAM in AI systems, right? So this is all for, we are building for AI hardware, right? Where such a memory is required, the area is very important, which we see now, and then the other things will come as a using this for weights and other things, let's say like inference, and so there are multiple ways that you can map the functions to these memories. So that is what you see is going to be becoming very important, and something to look for, right? And it may, you may see the commercialization also of this technology very soon, right? So that is the thing which we may see with this. Thank you. So keep learning. Happy going to all of you, and we'll see in the next video with more detail about another technology, what could be very interesting in the future. Thank you.